Hello. So now that we've derived the heat equation and have also established how boundary and initial conditions work for the heat equation, it's time to now actually learn how to solve it. And what we'll realize is that before we can solve it, we first have to, we, we, before we can solve it generally, we first have to just find the way we're going to approach this problem is we're going to just find a solution, an easy to find solution to this equation. And because the heat equation is a linear operator according to, like linear algebra, we can then treat that function as a vector and then take linear combinations of this easy to find solution to then generalize this to any solution. And if that didn't make sense, hopefully it'll make sense as we walk through an example. So let's let's um let's create a situation. We have our partial differential equation, which is partial u over partial t equals negative k times partial squared u over partial x squared. And we're going to assume no source charge or source heat to keep things simple. And then also for boundary conditions, we will say that at u at 0 comma t is equal to 0 and u at L comma t also equals 0. And this is, again, to just keep things simple and straightforward. And then finally, for the initial condition, we will say that u at x comma 0 is equal to some function f of x. So the key to finding a solution to this problem, a non-trivial solution to the problem, is through separation of variables. That is, there has to be some solution to this equation such that u of x comma t equals the multiplication of two functions, partial phi of x and g multiplied by g of t. What this then tells us is that we can rewrite this equation rather than as a partial differential equation, as an ordinary differential equation. So this becomes phi of x times the ordinary the ordinary first order derivative of g with respect to time. And likewise, this becomes minus k times g times the second order derivative of phi with respect to space. Now, rearranging this equation, we can get all the time-dependent terms on one side and all the x-dependent terms on the other side. And looking at this separation of variables, there's one key thing to notice. What that is that if we were to change time, as we change time, this side of the equation remains unchanged, right? As time changes, 1 over phi times the second derivative of phi with respect to x should not change because phi is not a function of time. So because this function remains constant as a function of time, this expression also has to remain constant as a function of time, and vice versa for the other side. Therefore, as time changes, both of these sides has to be constant, and as x changes, both of these sides has to remain constant. And we'll call this constant minus lambda. Uh, cool. Next, what we can do is we can separate this originally a partial differential equation into two ordinary differential equations by now saying, okay, 1 over kg times dg over dt is equal to lambda, and d squared phi, wait, hold up. 1 over phi times d squared phi over dx squared is equal to minus lambda. And here I just canceled out the minus signs that were on both sides, right? So solving this equation is pretty trivial. If you've done this differential equation before, you'll know that the solution ends up coming out to g is equal to c e to the k lambda t. Okay. C times e to the minus k lambda t. Likewise here, if you know how to solve a second order differential equation, what you do is you can describe it as a polynomial. You can describe the derivatives as a polynomial, and similarly, you will get phi is equal to e to the plus or minus I square root of minus lambda times x. All right. So first off, let's look at we want to look at these equations to kind of understand boundaries now. So g is equal to c times e to the minus k lambda times t. What we know is that as time approaches infinity, okay, what we can do is we can break this down into three cases. When lambda is less than 0, when lambda equals 0, and when lambda is greater than 0. So when lambda is greater than 0, then as t goes to infinity, g will go to 0, which is reasonable and physically not impossible. Likewise, when lambda equals 0, well, then g will just approach. Then as t approaches infinity, g will just equal c, which again is also physically not impossible. But then if we look at when lambda is less than 0, well, that means that the negatives in the lambda and the negative in the exponent term cancel, leaving us with a positive exponent term. And so as t approaches infinity, now g also approaches infinity, which does not make sense. And so we can rule out the fact that lambda is less than 0. We know that lambda is not less than 0. It has to be greater than or equal to, and really for all intents and purposes, greater than. So now what that allows us to do is we can then look to this section, because if we know that lambda, wait, no minus sign there, hold up. If we know that Because if we know that lambda is greater than 0, then that means if you solve this partial differential equation before, you know that there's three ways of writing this. For if lambda is greater than 0, then we have this imaginary term on the outside, and so we will get a solution of phi equals c sub 1 sine of x times the square root of lambda plus c sub 2 cosine times x square root of lambda. Like, similarly, if we take lambda equals 0, then we know that the general solution to this is c sub 1 is the trivial solution, c sub 1x plus c sub 2. And finally, if lambda is less than 0, then we know that then this becomes an imaginary number and cancels out with the imaginary number on the outside, and we get e to the minus x square root of lambda plus, or c sub 1 e to the minus x plus c sub 2 e to the x square root of lambda. Now, we already know from up here that lambda cannot be less than 0. And we also know from this, actually, that lambda cannot equal 0, because if it did, what we can do is we can look at our initial value problem, boundary conditions. So if we remember here, u at 0, comma t equals 0, which in other words, phi at 0 has to equal 0. And u of L, comma t equals 0, which in other words means that phi of L equals 0. And so if we plug these initial values into here, we will get the trivial solution. We will get the trivial solution that phi of x equals 0, which we do not want. We want the non-trivial solution. And so we know that lambda has to be greater than 0, and that this has to be the form of our space-dependent portion of our equation. So then what we can do is we can now use those initial boundary conditions that we came up with up here to figure out what the solution to this could be. So phi at 0 is equal to c sub 1 sine of 0, which is just 0, plus c sub 2 cosine of 0, which is 1. And this has to equal 0 according to our initial boundary condition. And so that means that c sub 2 equals 0. And so that means that there is no cosine term in our solution. Next, we look at phi at L, which is equal to c sub 1 times L square root lambda which equals 0. Or I forgot to write sine. But if we solve this equation, we can't get a value for c, but we can get a value for lambda. And we know from solving this, the lambda has to equal n squared pi squared over L squared. Or in other words, the square root of lambda, as is written in there, has to equal n pi over L for any integer n. Cool. So with these constants evaluated, we now have one of the solutions to our heat equation. That is U, which is equal to phi times G, is equal to, we'll call it a constant B times sine of n pi over L x times e to the minus k n squared pi squared over L squared t. Cool. And so this is just one potential solution of all the solutions again, right? And what that means is that what that means is that we now need to evaluate B and N given any certain initial condition. So for example, if our initial condition is U of x comma 0 equals, say, 4 sine 3 pi over L x, right? Which would mean that the temperature from 0 to L of the rod looks something like this. Well, then what we can do, we can plug 0 into here so that this becomes 1, and u at 0 has to equal b sine n pi over Lx, which means that which means b would equal, let's see, b would equal 4 and n would equal 3. And so this solution, if that was the initial condition, our solution would be 4 sine 3 pi over Lx times here times e to the minus k n squared pi squared over L squared times t. And this kind of makes a lot of sense because this is sort of our initial condition of how the temperature behaves. And then this shows how the temperature decays over time due to this exponential decay function. And so now we essentially know how to solve this problem if our boundary conditions are these prescribed temperatures of 0, and if our initial condition is a sinusoid, right? Which is kind of limiting, but it is a start. We now know how to solve, we now know one of the solutions to the heat equation. And this is useful because we can now use this one solution to generalize to all solutions because the heat equation is linear. And so we just take linear combinations of these solutions to get a general solution for any initial condition and any boundary condition, which uses something called Fourier series, and which we will see in the next video. Thank you for listening. Please subscribe and like the video if you enjoyed.